Okay, sorry about that, it got disconnected. Okay, so this Biot-Savart law, we can just substitute the respective parts and we get that the magnetic field, that's our B, because of one vertical side, okay, we can just take it as our AD, will be equal to our mu naught upon 4 pi, and this comes as our IA sine of theta upon r square, and we substitute value of sine of theta. So this comes as mu naught upon 4 pi, and this is our IA upon r square, sine of theta is our a by 2 upon r. Therefore, we get that magnetic field because of one side, that is of AD, will be equal to, this comes as our mu naught IA square, and we have this as 8 pi r cube. Okay, so we have two vertical sides, therefore we can write that magnetic field due to vertical sides will be equal to twice times our, because of our one side. Therefore, this comes as our mu naught IA square and 4 pi r cube. Now we can find out the total by combining this horizontal as well as the vertical. Therefore, we can say that net magnetic field, that is our B, will be equal to magnetic field because of the horizontal and magnetic field because of the vertical, and their sign will be obviously our, one will be our into and other will be the out of the paper, so we can take any type. Positive, obviously they are going to have opposite sign, so this comes as our mu naught I a square and 2 pi r cube minus mu naught I a square 4 pi r cube. Therefore, we get that the total magnetic field B will be equal to our mu naught I a square, and this comes as our 4 pi r cube. So this is a net magnetic field because of our square. Next question. It states that a solenoid is made by winding two layers of number 14 copper wire on a cylindrical form, 8 cm diameter. There are 4 turns per centimeter in each layer, and the length of the solenoid is 32 cm. From the wire tables, we find that number 14 copper wire, which has a diameter of 0.163 cm, has a resistance of 0.010 ohm per meter at 75 degree centigrade. If the solenoid is connected to 50 volt generator, what will be the magnetic field strength at the center of solenoid in Gauss, and what is the power dissipation in watts? Okay, so there is no need to worry about this particular number because the data is with respect to this wire is already given in the question, that is the diameter as well as the resistance. Okay. So first of all, we are having an inner layer as well as the outer layer. Okay, so we are mainly interested in finding out what will be the average diameter. Okay. So we start with our average diameter calculation. We are having an inner layer and This inner layer is that it winds on a 8 centimeter form. It winds on 8 centimeter form. Therefore, we can say that the diameter, which is suppose our D1, is our 8 centimeter. And next is our outer layer. And this outer layer, it winds over the inner layer. Okay, it's wound on the inner layer. Therefore, we can say that the approximate radius, or we can write this as a center line at the radius, center line at radius is our R0 plus T. Okay, these parameters given to us. R0 is given to us as 4 plus T is given to us as a 0.163, and this comes as our 4.163 centimeters. Therefore, we can write that the diameter for the second layer, that is our D2, will be equal to our inner plus, and this comes as our 8 and 1 second. Yeah, it will twice into 0.163, and this comes as our approximately will be equal to 8.3 centimeters. Therefore, like we said, that the inner diameter is our 8 and the outer layer is resulting in our 8.3. So we can just approximate it as to be our 8.3. Okay. Therefore, we can write that our average diameter, which is our D average, will be equal to our 8.3 centimeters. Most of the time here it is not mentioned, but sometimes in the question itself it mentions that the actual value of diameter which have to takes place. And from here we can find out the circumference per turn. Circumference per turn, and let us suppose that is given as C, and that will be equal to pi times 8.3, and this comes as our 26.08 centimeter per turn. And now we have to find out our, because we are mainly interested in finding out the power dissipation. Okay, and for that we will be requiring this resistance. And for resistance, because the resistance that is mentioned in the question is given as a per meter, so we have to find out what will be the total length. Okay. And for that we are going to use our number of turns as well layer and per layer. Okay. Therefore, we can say that the wire length suppose that is given as our L total, then this total wire length, because will be equal to number of layers, which is our 2 in this case, multiplied by length per layer. Length per layer. Number of layers is 2, so we are mainly interested in calculating the length per layer, and for that we are given that the turns per layer are 4. Turns per layer is given to us as a 4 turns per centimeter and multiply by 32. So which comes as 128 turns per layer. Therefore, we can write the length per layer, and that will be equal to 128, and this comes as our circumference is 26.08. So this approximately will be equal to our 3340.76 centimeters, and therefore length total which is our number of layers multiplied by our this length per layer, which is our 3340.76, and approximately this will be equal to our 67 meters. So now we can easily find out our resistance. Therefore, we can say our resistance, whichever R, and we are given a per meter resistance, that is 0.010 multiplied by the total length, that is 67. So this comes as 0.67 ohms, and it is connected to a 50 volt source. Therefore, we can say the current, which is our I, is equal to our 50 and 0.67, which gives us approximately as our 75 amperes. Therefore, we can easily find out our power. So you can say our power, that is our P, is equal to our V times I, and this is our 75 and times our voltage given to us our 50, and this is approximately will be equal to 3750 watts. So this is the value of our power, and we can find out our magnetic field. So we can say that the infinite solenoid magnetic field, which is suppose our B infinity, and this B infinity, the standard formula is our mu naught n times I, and mu naught is our 1.25 into 10 to the power minus 6 multiply by 800 and multiply value of our current, that was approximately as our 75, and this comes as approximately as 0.07495 Tesla, but we are supposed to find out in Gauss. Therefore, we can say that this will be equal to our 0.07495 into 10 to the power 4, or approximately we can say this is our 750 Gauss. So this was our the magnetic field that was required. Okay. Here only minor discrepancy is, or we can say, because the question language is not clear basically. So because we have two layers, and inner is our 8 centimeter diameter and outer is close to our 8.3 centimeter. So we took the average as 8.3. Okay, normally in the question it should have clearly mentioned that what value of diameter, or they should have given some hint. So the entire calculation is based on this average diameter which I have taken. Okay, if it comes a little bit different, sometimes it comes like 8.25 or 8.22, so 8, or rather we can say 8.29 also. So this calculation will be a little bit left to right, but basic concept is going to remain same. Okay, so we have to take care of that, okay, because the rest of calculation is quite simple here. Only minor confusion point is that what should be the value of the diameter. Okay, because based on diameter we can easily find out what, because we are interested in finding out meaning the resistance, and for resistance we need length. Okay, and this diameter is helpful in finding out the circumference. Okay. So the next question: a very long cylinder with radius r and uniform volume charge density rho spins with a frequency omega around its axis. What is the magnetic field at a point on the axis? How would your answer change if all the charge were concentrated on the surface? Okay, so this is quite simple, not much of things required. So first of all, basically we are going to find out our current density, and then we can use our Ampere's law in case of rectangular loop and get the answer. Okay. So let us solve first of all for part A. And part A, we are interested in finding out we first find out our current, and that is going to help us to find out the magnetic field. Okay. And so we can assume that, let us suppose there is a thin ring of radius r and thickness dr and length is our L. You can say for a thin ring radius r, thickness dr, and the length is L. Okay. Therefore, we can write it's our charge. So we can say our charge, because of this ring, our dq, and this dq will be equal to the charge density, and because of thickness and radius and length, we can write this as 2 pi r dr times L. And now it is given that it is having an angular speed of omega. From there we can write the linear speed. Therefore we can say that the speed v will be equal to omega times r. And we can also write the time for one revolution, time for one revolution. If that is our capital T, then this capital T will be equal to over 2 pi upon omega. Therefore, current due to the ring, that is our di, will be equal to over dq upon time t. Okay. So we simply substitute the values. We get this as our rho 2 pi r dr times length L, and t is our 2 pi upon omega. And this 2 pi and 2 pi cancels out. Therefore we get that the current due to this ring, that is our di, will be equal to current density omega RL times dr. From here we can find out our current density. Therefore we can say our current density, that is our J, is our current d of I and L dr, which gives us rho omega times R. So you got the value of the current density. Okay. And we can use our Ampere's law, which states that for a closed surface, our magnetic field dot dl is equal to mu naught times the current enclosed. Okay, that is our Ampere's law for a rectangular loop, a closed surface. Okay, because here we are having a cylinder, so we can consider a surface which is somewhat like a rectangle. So we consider that a rectangle one second. So okay, let me write in this way, because we are using the Ampere's law. And for that we consider rectangular loop. And for this rectangular loop, we consider its side along the axis length L. You can say our rectangle side along axis length L. Axis length L, and at a distance R, which is greater than the radius of this cylinder. Okay. So we can write the equation that our Ampere's law for a closed surface will be B dot dl will be equal to our mu naught and the value of the current, which is basically enclosed. And we are supposed to find out this line integral, and this line integral will be giving us, we are interested in this line integral, this part. So we can say our line integral. So we are having a axis side, and this axis side is our B dot L, and we have considered this because our outside side the magnetic field, our outside will be equal to 0, because just like a solenoid, and our radial side our magnetic field will be perpendicular to the element, that is dl, which gives us value of 0. Therefore we can write that this our line integral will be equal to nothing but our BL. Okay, because it is going to have three components. First is the axis side, which is BL, outside which the magnetic field is equal to 0, just like a solenoid, and the radial side, because it is a dot product, so they are perpendicular to each other and gives us a value of 0. So their addition will be just equal to BL. That is, line integral is equal to our BL. And so now let's find out what will be the value of the enclosed current. Okay. We can see enclosed current And for that we consider a strip whose radius is small r and the width is our dr and its height is our L. Therefore, we can say the current through the strip which is a small current, our d of I, and this is for our strip, will be equal to our current density times our length, and its thickness is our dr. And current density we already calculated. Therefore, we can say that our current through the strip will be equal to our rho omega r times length times dr. So it means the total current, that is a current enclosed. Okay, so we can say that our total enclosed will be equal to our I enclosed, and this we can write integral for this our d strip, and it is going to vary from 0 to r. We substitute value of this d strip, so we can say current enclosed will be equal to our 0 to r rho omega r, and this is I dr, and this will be coming as our, because only is our r, this will be r square and giving us capital R square. Okay, so we get this our current enclosed will be equal to our rho omega L times r square by 2. So we come back to our Ampere's law. Our left side is our BL and right side we just calculated our current enclosed. Therefore, we can write that our B times L will be equal to our omega rho omega L r square by 2 and multiply by mu naught. Therefore, we can say that the value of magnetic field B, L and length cancels out, so it's quite simple now. So this comes as mu naught, and this is omega rho and r square by 2. So this is our value of our magnetic field. And now we come to part B, and in which states that the surface, entire charge is on the surface. Part B. Okay. So in this case we are going to start from our surface charge from the volume. So we can say our charge per unit length, and so we can write that our one second. Yeah, I think we can do it like this. Okay. So we have our charge per unit length volume is our lambda is equal to rho pi r square, and we can also write our surface, which is our lambda is equal to our sigma and 2 pi r, and therefore we can say that our rho pi r square is equal to our sigma 2 pi r. Therefore, we get our sigma is equal to rho r upon 2. Okay, so we got the relationship between our surface charge as well as the volume charge density. Okay. Now we come to our surface current. Surface current, and for that we know that it is rotating with the speed of omega, so we can say speed at the surface, speed at the surface, which is v, will be equal to omega times r. Okay. And our surface current density, surface current density, let us suppose that is our k, will be equal to the surface charge density multiplied by the speed. So this comes as a rho r upon 2 times omega r. So we get our surface current density, that is k, is equal to rho omega r square upon 2. And because this is a infinite cylindrical, so we can just use you can say the effect of a solenoid. So we can say infinite cylindrical current sheet. Infinite cylindrical current sheet. Okay. And that will be our equivalent to our solenoid. Solenoid with n times I, and that is nothing but our k. Therefore, we can write that the magnetic field inside will be equal to our mu naught n times I, or we can say this is nothing but mu naught times k. And we substitute the value, we get this as mu naught, and this is rho omega r square by 2. And if required, we can also solve it by using the shell method. We consider a thin shell of radius r dr surface current, and then we can simply integrate it. Okay, so that is going to give us the same answer. Okay, it's not going to change. So these were the 4 questions from the chapter magnetic field. And this completes for today. Thank you.